Should be intake 2.
So where
Well,
where is the semester ending?
semester will never end.
Which topic?
That topic
End of electricity.
Yeah, end of electricity. Here, let me show you. Yeah, we have 9 topics to do in electricity.
Yeah.
Yeah. Let's get started. Charge and current. Oh yeah, it's pretty good. What?
So really wanted someone who just it's
No. Mine. Okay. Charge and current. You got that?
yeah.
Let's do. Right. So, from chemistry, you know that electric charge is a basic property of electrons and protons. Electrons are negatively charged and protons are positively charged, right? Yeah. Things that are negatively charged and things that are positively charged, they pull and attract on each other. This makes the electrons and protons stick together. Things that have the same charge push each other away. This is called the law of charges. Now you don't need to write that. No, you don't need to write this down. This is just reviewing something you know from chemistry, I hope. Yeah. I really hope you know this from chemistry, right? Pretty basic. Okay, so now what's new for physics? We say an electric current is a flow of electric charge. In a metal, it is free electrons that flow. Now, have you talked about that in chemistry? In a metal, you have free electrons. Yeah. And these electrons are what move. And this is what makes a current. So you should write this definition down. Okay, have you got that? Yep. And there's a little picture of it. That's pretty easy, right? Yeah. So, does anybody know what an electrolyte is in a chemistry context? What do you think it is, Rodman?
The source of the total.
Yeah, close, yeah. What? Yes. What are they? An electrolyte is a chemical that conducts electrical current. It's used in batteries, like you said, Marwan, to make ions flow, producing a current. Now, you don't need to write the next part down. You all know what an ion is, don't you?
Yes.
What's an ion? Ions are just atoms with extra or missing electrons. So it's enough to write this much down. Yeah? Okay, have you got that? No. What? What? Leave Bello alone. Don't pick on him. Yeah, you. He's not wasting pages. Yeah. Are you, Bello? Right. Have you got that? Yes? Okay. So, have you seen this diagram in chemistry? In chemistry this year? Okay. Maybe. You think not, though? Huh? Oh, really? Next class? A future class, okay. I think it'd be... Now, we don't really need to worry too much about this in the physics, okay? But since you're doing chemistry, it might be a good idea to have this as an example of an electrolyte. So, can you see in the picture here? I don't know if you can tell, these are positive. This is 2H+. Cu is... What's Cu? Yeah, and Zn? 3. And what's happening here? Oh, and this... You've done this in chemistry, H2SO4, haven't you? Yeah, what is it? It's a strong acid, isn't it? Yeah. So, this can make a current. The positive flows this way and the negative flows this way. So this becomes positive and this becomes negative. And the positive has a name. Well, I don't know. I thought... Are we talking about the name of these or the name of the plates? This one is cation, isn't it? Or this one? Are you sure?
No, because this one is attracted to negative. And negative attracted to positive.
Yeah, I thought...
That means the one with the cation, copper is the anode and zinc.
Yeah, I thought so too. I thought this was the cathode, and this is the anode. Yeah, okay, all right. So I know you're confusing me, but I think I think I'm right. This one is the cathode, and this one is the anode. Okay, fine. Okay, draw this and include the name, please. Cathode and anode. I hope so. Wherever I got this from, I hope they were right. Got that drawn? Huh, which?
Under the SO4.
Yeah, that's a minus.
Under it.
That's a plus.
Yeah, isn't it supposed to be like H not Zn?
No, I think the zinc is getting pulled off of this. And then it attaches here. You might have seen this before, it changes colour. And the size too.
There was a bridge in front of, in middle.
Yeah. Is this okay?
Yes.
Yeah. Continue?
Yeah.
Yeah, okay. So, which way should we say the current flows? So in this diagram here, do we say it flows from positive to negative, or from negative to positive? It's both. So, so let's be clear. In this picture here, we say the current flows from positive to negative, but actually the electrons flow from negative to positive. So just to be clear, if an electron moves from A to B, we say there's a current flowing from B to A. Yes, B to A. I know this seems a bit confusing. Yeah. I think this diagram would be good. Can you see that? That's current and that's electron flow. Yeah. Okay, you got that drawn? Got that? Oh, I'm so busy. Continue? Oh, okay. Okay, you got that? Okay, continue. Why is this way? Well, it's a long story, but the problem is because we call electrons negative and protons positive. And you might say, well, aren't electrons negative and protons positive? Well, which hand is this? My left or my right? Left. And which one is this? Right. But everything would be okay if we all swapped the words, right? If I said this is my left and this is my right, if everybody did that, would we have a problem? No. No. Likewise, if everybody called electrons positive and protons negative, there'd be no problem. Because the only thing that matters is if they're the same or opposite. Why does an electron and a proton move together? It's only because they're opposite. Yeah, that's all. It doesn't matter if you call one of them positive and one of them negative. It's just a name, you know. So this is kind of this is the reason why it would have been better if electrons were called positive, you know. So in some parallel universe, perhaps people do this. And the reason we can thank for this is Benjamin Franklin. But anyways, it's a long story, but it's you know Benjamin Franklin, the guy with the kite in the thunderstorm with the key in the jar. Do you know this guy? You don't know him? You know him?
The funny hairstyle.
Yeah, some people know him. Anyways, he's the one to blame for this mess. But that's the way it is. Now, I'm going to give you the definition of 1 amp. You might have heard of an amp before. Yeah? Amp is short for ampere. Yeah? 1 amp is, now, the definition is very difficult. Very difficult. It's the good news is they've only asked this definition once in the exam. Yeah, but just once. In the last, like,
20 years.
no, maybe about 15 years.
So don't remember that.
Well, there's 2 exams every year, so 15 years actually means 30 IFYs. So it's 1 per 30 IFYs. Probably be okay. Yeah. 1 amp is the current that will produce a force of 2 times 10 to the minus 7 newtons per meter between 2 straight parallel conductors of an infinite length and negligible cross-sectional area 1 meter apart in a vacuum. So, let me explain that. Imagine you have a piece of copper here, and you have a piece of copper here, and there's a current, there's a flow of electrons here, and there's a flow of electrons here. Now you know that there's going to be forces, isn't there? Electrons, you know, and protons and all this, they interact, positive, negative, and so on. So, if you place them 1 meter apart, and you get this much force, 2 times 10 to the minus 7 newtons, then you say you have 1 amps. Now, you might say, why is this definition the way it is? It's a very strange definition. It's a technical definition. It's not really a useful definition. You know, for me, there's 2 types of definitions, technical and useful. So like a useful definition would be 1 Newton causes 1 kilogram to accelerate 1 meter per second squared. Or 1 Pascal is 1 Newton per meter squared, right? These are useful definitions. This is not a useful definition. This is a technical definition. I'm nearly saying that. So, write it down, but I know 90% of you or higher will not remember it. We just have to take the chance that they don't ask it. Okay?
But you did know how many you 1 mark, right?
1, maybe 2. Yeah, I think I would give up the 1 mark too, maybe. I tell you, if it was 2 marks, I would only get 1 mark because I would forget that the number was 2 times 10 to the minus 7. Every time I think I'll remember it, I forget. I'm like, is it 2 or was it 3? Or was it minus 7 or was it minus 8?
Remember all the conductors of infinity?
Yeah, actually I can remember that and not the number, if you can believe that. I know, I'm weird. I'm a weirdo. Most physics and maths teachers are weirdos, so it's normal. Oh no, need a second, huh? Got that?
Yeah.
Good. Remember it? No. But I showed you, so. Yeah. By the way, is 1 amp a big or a small current? What do you think? It's actually, you know, it's pretty big. It's pretty big. I mean, 1 amp would be, I don't know, like maybe this computer would use 1 amp, or the, okay, maybe not the projector. The projector would be pretty high, I'd say. Phones, yeah, phones. Oh yeah, phones would definitely be 1 amp current when they're charging. Yeah. Tablets, laptops, computers, game consoles, these would all be 1 amps. The only things higher than 1 amp would be like, you know, electric shower, electric heater, microwave oven. Huh? Yeah, things that produce heat, really. But 1 amp is pretty big. I think a fridge, oh, maybe it's, I don't know, 4 or 5 amps maybe. I don't remember. It's not too bad. Still pretty big though. Okay. Now, the Coulomb. The Coulomb is how we measure, the symbol is C, it's how we measure charge. And the definition of Coulomb is quite simple compared to the last definition. A Coulomb is the charge you have when you have 1 amp for 1 second. So if you have 1 amp for 1 second, you have 1 Coulomb. So as a formula, you have charge equals current multiply time. Okay. Say again? Oh yeah. Yeah, it's weird actually. I think that's right, because the first unit is a proper noun. It's the name of the body, International System of Units. And the second unit is a noun. So I think that's fine to have actually. It's like, Bello, if I had a restaurant called Lunch, and I said to you, how's Lunch's lunch? It's a bit like that. Okay, have you got that? Yes. How big is 1 Coulomb of charge? It's actually pretty big. And the way you can see this is because I'll tell you what the charge is of an electron. The charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. And often we just write that as minus E. Not to be confused with the E in maths. It's not the same E. Okay? In chemistry, you simply just call this charge minus 1. Right? Like if you're in chemistry class and someone said, what's the charge of 2 electrons, you would say -2. Okay? Yeah? But we use the unit coulombs. And for us, this is how much of a charge an electron is. And on the list of constants, it uses the letter E. But like I said, this is not the same as the maths E. Remember the maths E? 2.7? It's not that. Okay. Can you write this value down? Yeah.
So is the Coulomb the delta Q?
Yeah.
What's that C? The symbol is C. Like.
The C is the unit. Oh, you're saying why don't they use a C here? Yeah, but I mean, force is F. So it's not N. Do you know? Yeah.
So we say 1 Coulomb is equal to -1.6
-19 coulombs is 1 electron charge. Yeah? You got that? Yeah? Okay. Here is a super easy question. 100 milliamps flows for 2 seconds. What's the total charge? Well, you only had one formula. What's our formula? Q equals IT. What's the I? Is it 100? 0.1. And the T? 2. So therefore the total charge? Easy peasy. Right? Don't worry. It gets harder. We've just started the chapter. Okay? And there's probably only like, I don't know, what is there, 2 questions or something in the database? How many's there?
2.
There is only 2? Yeah? Yes? Okay, so look, just take, 2 minutes to do 2 questions, and then we'll start the next lesson.
But that's the example given us this question.
It's as easy as this. Just one formula. Q equals IT. Yeah, it's so easy. Too easy. Too easy. What?